Today, we're going to follow a single piece of data on its actual physical journey from one place to another. We're going to peel back all those abstract layers of the cloud and look at the real-world wires, glass, and airwaves that make our digital lives possible. Let's get into it.
Think about it. We do it dozens, maybe hundreds of times a day without even thinking. You hit send, and poof, your message is gone. It just reappears a few moments later, maybe across town, maybe on the other side of the planet. But here's the thing. It doesn't just teleport. It travels. So what does that physical trip actually look like?
You know, when you boil it all down, the process is actually pretty simple. It doesn't matter if you're sending an email, streaming a movie, whatever. All data starts at a source, travels through what's called a transmission medium, and that's our focus today. And it arrives at a destination. It's the oldest story in communication, just told at, well, the speed of light.
Okay, so our journey begins right here, close to home, on what you could call the local roads of our network. These are the physical cables plugging your computer into your router or connecting all the devices in an office. They are the absolute first step for any piece of data going anywhere.
I bet you've seen this cable before, right? It's the one that probably connects your TV or your cable modem. This is coaxial cable, or coax. At its very center, there's a copper wire that carries the data. But the really important part is what's wrapped around it. You've got this plastic insulation and then a braided copper shield. That shield is key. It protects the signal from all the random electrical noise out there, making it a really sturdy and reliable path for your data.
All right, now let's talk about one of the most common cables in the entire world, your standard Ethernet cable. Its technical name is Unshielded Twisted Pair, or UTP. So why the twist? Well, this is just a brilliant but super simple bit of engineering. Imagine a magnetic field from a power cord hits the cable. Because the wires are twisted, that interference hits each wire in the pair equally, but in opposite directions. So when the signal gets to the other end, the device sees these two perfectly opposing interference signals, and they just cancel each other out. It's such an elegant solution, and it also keeps the different conversations in each wire pair from bleeding over into the others.
But what if you could just get rid of the electricity problem altogether? Well, that is the absolute magic of fiber optics. Instead of pushing electrons down a copper wire, fiber sends tiny pulses of light down a strand of glass that's as thin as a human hair. The light literally bounces its way down the cable, reflecting off the inner wall, which guides it perfectly. It's less like a highway and more like a bobsled track for your data, running at the speed of light.
So when you put them head to head, it's really all about choosing the right tool for the job. Fiber gives you insane bandwidth over huge distances, and it's completely immune to the electrical noise that plagues copper. But that top-tier performance comes with a bigger price tag. On the other hand, copper is way cheaper and it's everywhere, but it's slower, it can't go as far, and you always have to worry about interference.
Of course, not all data is content to just stay inside a cable. The next leg of its journey very often involves making a leap right through the air. So let's take a look at how our data goes wireless.
Just like there are different types of physical cables, wireless data has different ways to travel too. It rides on electromagnetic waves. For what we're talking about, the three main carriers are radio waves, which you know from Wi-Fi and Bluetooth, microwaves, and infrared. They're all part of the same big family, the electromagnetic spectrum, just different frequencies with very different abilities.
Let's zoom in on microwaves for a second. They're fantastic for sending a ton of data, but they have one major rule. They only travel in perfectly straight lines. This is what we call line-of-sight transmission. If anything, a building, a mountain, even just the curve of the Earth gets in the way, the signal is blocked. Dead stop. So, how in the world do you send a microwave signal across the country? We cheat. That's how. We put a giant relay station way up in space. A station on the ground beams the microwave signal up to a satellite, and the satellite just catches it and beams it right back down to another station maybe thousands of miles away. It's basically a giant mirror in the sky that lets us bypass any obstacles on the ground and bend the signal's path around the planet. And now for the shortest hop on the wireless journey, infrared. We use this every single day with our TV remotes. And its biggest weakness is actually its greatest strength. Infrared signals cannot go through walls. And that's a good thing. It means when you go to change your channel, you don't accidentally change your neighbor's channel too. It makes it perfect for secure, short-range communication that's contained to a single room.
Okay, so our little packet of data has navigated the local network. Maybe it's even jumped through the air a bit. But to get from, say, New York to Tokyo, it needs to get on a global data superhighway. These are the specialized wide area networks, or WANs, that form the real backbone of the internet, connecting different networks across huge distances. Let's take a quick trip back in time. One of the earliest of these global highways was called X25. The best way to think about it is like an armored truck. It was designed back in the 70s to send data over old, crackly, noisy, analog phone lines. So its number one priority was reliability. It was packed with tons and tons of error checking to make absolutely sure the data arrived safely. This made it incredibly dependable, but also painfully slow.
So fast forward to the 90s, and the world is changing. Those noisy old analog lines are being replaced by clean, digital lines, a lot of them fiber. This huge improvement in the underlying roads allowed for a new technology, frame relay. It basically made a very smart bet. It said, hey, since the roads are so much better now, we don't need the armored truck anymore. So it stripped out most of that heavy error checking, which slashed the overhead and massively boosted the speed. It's a great example of how the whole system gets faster when the physical layer gets better.
Next up was a really ambitious idea called Asynchronous Transfer Mode, or ATM. The goal here was to create one single unified superhighway for all kinds of traffic. Data, voice, video, you name it. Its secret was the cell. It chopped everything, and I mean everything, into identical, tiny 53-byte packets. Because every packet was the exact same size, traffic became super predictable. And that allowed the network to actually guarantee quality for things that can't be delayed, like a phone call, which was something other networks really struggled with.
And of course, we can't forget the OG global network, the public switched telephone network. Yeah, the good old phone system. We think of it for voice calls, but today it's this massive, almost entirely digital global infrastructure. For decades, it provided the physical pathways for stuff like dial-up internet, and really formed the bedrock that a lot of these other long-haul technologies were built on top of.
So, after traveling on all these different roads, rails, and airwaves, our data is finally closing in on its destination. Let's just take a second to recap the incredible physical path it might have taken.
I mean, it's really a mixed-mode journey, isn't it? Your email could have started on a copper Ethernet cable, jumped to a fiber optic line under your street, then beamed up to a satellite, crossed an ocean on a subsea cable, and then done that whole process in reverse to arrive. Every single step of the way, it's a real physical signal moving through a real physical medium.
So the next time you hit send, just take a second to appreciate that incredible physical trip. From the clever twists in a copper wire to the light in a glass fiber, to relay stations literally orbiting our planet, our seamless digital world is built on this breathtakingly complex and very tangible physical foundation. And it just makes you wonder, right? As our demand for data and speed just continues to explode, what amazing new physical pathways are we going to invent next?